This remarkable display of colours and shapes is what you see when you look at a thin section of a coarse-grained igneous rock between two Polaroid sheets in a petrological microscope. The bright colours are produced by crystals of olivine and pyroxene, and the grey shades by feldspar crystals. Those colours are called interference colours, and we can use them to help us identify the minerals in the rock. But to do that, you need a polarizing microscope. It's fitted with two pieces of Polaroid, one below the specimen called the polarizer, the other one above it called the analyzer, that you can move out of the system if you want to. Now, most people are familiar with Polaroid sunglasses. They cut down the glare you get from reflecting surfaces like water and shiny roads. And they do that because they only allow light through that's vibrating parallel to a particular plane of polarization of the permitted direction. And there's another effect you may have seen, which you can get with two pairs of Polaroid sunglasses. If I rotate one lens in front of the other, I can cut the light out completely. And that happens when the two permitted directions are at right angles to one another. And that's the arrangement of the Polaroid pieces in the polarizing microscope. Now, in order to show you how to use an instrument like this to identify the minerals in rock-thin sections, I'm going to use a very simplified model of the polarizing microscope. At this end, we've got a light source, two sheets of Polaroid, and at the other end, a TV camera, which acts as an eyepiece. The arrow on this Polaroid sheet tells you its permitted direction. The light passing through that is polarized parallel to this plane. We call that the east-west direction. The arrow on this Polaroid sheet tells you that the permitted direction is at right angles to the other, that's north-south. And obviously, with only one sheet of Polaroid in the system, you get some light passing through to your eye. I can cut that off by putting the Polaroid sheet back again, just as with the sunglasses. When the Polaroid sheets are in this position, we say they're crossed. Now, the air between the sheets is isotropic. Like all gases, it has no effect on the passage of polarized light. If I move a sheet of glass about between the Polaroid sheets, again, there's no effect. Glass has no definite crystalline structure, it's isotropic. And in fact, you'll find there are a few crystalline minerals that are isotropic as well. But the great majority of minerals are not isotropic. This is a sheet of the mineral mica. This rectangular shape we got by cutting from a larger cleavage piece. Now, when I move this about between the two sheets of Polaroid, some light very definitely gets through to your eye. The mica interacts with the polarized light to give you this splendid display of colors. Now, most minerals behave like that if you get them thin enough when you view them between two sheets of Polaroid in the cross position. Minerals like that are called anisotropic minerals. Now, watch what happens when I hold this sheet of mica parallel with the Polaroid sheet and rotate it. It goes dark 1, 2, 3, and 4 times in a complete rotation through 360 degrees. Now, those dark positions are called extinction positions, and they happen at 90-degree intervals. Now, all anisotropic minerals show that effect. All anisotropic minerals will give you 4 extinction positions, 90 degrees apart, in a full rotation when you look at them between sheets of Polaroid in the cross position. And we can explain that if we suppose that all anisotropic minerals, like this mica, can themselves polarize light into 2 mutually perpendicular directions. Let's see how that works. Light coming through the first Polaroid sheet is polarized in the east-west plane. It can't get through the second Polaroid sheet because that only lets light through that's vibrating in the north-south plane. But when we put the mica sheet in with its 2 polarization directions east-west and north-south, still no light comes out of the second Polaroid sheet. The mica is in extinction. And in this position, the mica doesn't affect the passage of the polarized light. If the mica is rotated through 90 degrees, it's again in extinction because its two polarization directions are once again lined up with those of the Polaroid sheets. Rotate it a further 90 degrees and we see the same effect. Well, that does seem to explain some of what we see. But now let me show you that anisotropic minerals really do polarize light in two mutually perpendicular directions. This is a natural cleavage ROM of the mineral calcite, a special transparent variety called Iceland spar. Calcite is anisotropic. So when I put it over this dot, you see two images. You see two images because of double refraction. Now the light rays corresponding to one of those images is polarized into one plane, and the light rays corresponding to the other image are polarized in a plane at right angles to that. Now that being the case, I can make those images disappear and reappear by rotating a sheet of Polaroid over the calcite ROM. Now let's just look at that a little bit more closely. That's the permitted direction of the Polaroid sheet. If I hold it over the calcite in that position, only one image is visible. And that must mean that the light corresponding to that image is polarized to vibrate in that plane. And if I turn that through 90 degrees, the other image appears and the first one disappears. And that means that the polarization plane of the second image must be like that. So we've got two directions of mutually perpendicular polarization. Now, all anisotropic minerals have that effect, but calcite's the only common mineral that shows it anything like so well. Now, there's another very important aspect of double refraction, and it's this. The light rays corresponding to those two images travel along different paths through the crystal, and they travel at slightly different speeds so that one set of rays lags a little bit behind the other. And that lag we call a path difference. And it's that path difference that's responsible for the interference colors that you were looking at earlier. The light that leaves the first Polaroid sheet is polarized into a single plane. When it passes through a mineral that's not in its extinction position, the light that emerges is polarized into two mutually perpendicular directions by the mineral. These are then polarized back into a single plane by the second Polaroid sheet. Now this light's still actually made up of the two rays that travel through the mineral at different speeds. So one ray is lagging behind the other. There's a path difference between them. If that path difference between the two waves corresponds to a whole number of wavelengths, then the crests will coincide so that the two rays reinforce each other, and you get constructive interference. But if the path difference between the two waves corresponds to an odd number of half wavelengths, then the crests of one wave will coincide with the troughs of another, and the two waves will cancel each other out. That's called destructive interference. So the effect of interference is to produce either light or darkness. The first dark band corresponds to a path difference of half a wavelength, the first light band to a path difference of a whole wavelength, and so on. And this is the effect of variable path difference when we use light of only a single wavelength. But in the microscope we use white light, and white light's a mixture of wavelengths. So instead of seeing alternating light and dark bands, you see this repeating pattern of the rainbow colors in the spectrum of white light. This progression of colors is the result of increasing path difference in anisotropic minerals. And in standard thin sections, we keep the thickness constant, so the path difference depends only on the amount of double refraction in the mineral. And in fact, in most of the minerals we're dealing with, the interference colors in standard thin sections will correspond with the lower part of this chart. But you won't see interference colors at all if you can't get rocks and minerals thin enough to see through. And up until about the middle of the 19th century, geologists had to make observations on rocks and minerals using only the naked eye or the hand lens. Till about 1850, when Henry Sorby, a scientist living in Sheffield, found out how to grind rocks thin enough to see through and to mount them on microscope slides. And this magnificent brass instrument is the very microscope that Sorby himself used. And here is one of Sorby's original thin sections. It's of a granitic rock from Aberdeen, beautifully made, and he's even engraved the locality on it and the year in which it was made, 1858. And today, thin sections of rocks and minerals are made by the same methods used by Sorby. There's a large thin section preparation laboratory on the campus of the Open University, which is equipped to make large numbers of slides for students studying geology courses. First, massive amounts of rock have to be gathered. Granites and basalts and many other different kinds of rocks are collected from all over Britain and sometimes from overseas as well. It's very important that the specimens are fresh and quite large so that many identical specimens can be produced. These large lumps are then broken down into smaller pieces. An automated diamond-edged saw is used to cut them into a series of 2mm slices. It's important, even at this stage, to get a slice which has a constant thickness and which is as smooth as possible. The slices are then lapped and cut into smaller slices, ready for mounting onto a glass slide. A warmed-up epoxy resin is used to cement the rock slice to the slide, and it's very important that they're pushed firmly together so that no air bubbles are trapped in the resin. Both the glass slide and the resin are isotropic, so they won't have any effect on the light that passes through them. Now, the next step is really the most difficult and the most important. The rock slice is now ground down in stages to a uniform, very thin layer of about 100 microns. The first few layers are removed with a carefully adjusted surface grinder, which can pass over 120 specimens at once. The thin sections are often finished manually by grinding them face down on a glass plate with a fine abrasive powder to get a uniform thickness of exactly 30 microns. It's very important to be able to grind any rock thin sections to this thickness so that the optical properties of the different minerals can be accurately compared. And this final thickness is controlled by observing the interference colors of a common mineral like quartz, which is present in a large number of rock types. And if you like, before you put the thin section on the microscope stage, you can look at it between two sheets of Polaroid. The interference colors show up the different grains, and they change as you move the slide about. It gives you an overall view of the texture. This is the main microscope room of the Earth Sciences Laboratory at the Open University. And I'm going to use this rather impressive instrument. It looks rather different from your microscope, but it has exactly the same basic components. A light source, polarizer underneath the stage, rotating stage, analyzer out and in. There's a binocular eyepiece on this instrument, and here a TV camera that's linked to this screen so that you can see what's going on. And that's why I'm going to use this instrument. So let's take a look at this thin section. As I rotate the stage with the analyzer in, you can see at once the irregular, interlocking texture of the mineral grains in this crystalline rock. It's a granite. Now, all the minerals in this rock are anisotropic. They all have 4 extinction positions, 90 degrees apart, in a full rotation of the stage. Each grain goes into extinction when its polarization directions are parallel with those of the polarizer and the analyzer in the microscope. And the minerals in this rock are obviously in all sorts of different orientations, and that's typical of a great many rocks. All rocks are 3-dimensional aggregates of minerals. And any thin section through a rock like this granite will give you a 2-dimensional picture of it. And because the mineral grains are in random orientation in the rock, the thin section will cut through them in every conceivable direction. And what I want to show you is the effect that that has on the way that minerals look when you see them down the microscope. Now, with the analyzer out, most of this thin section is colorless, except for these brownish crystals. Now watch what happens when I rotate the stage. They change color between lighter and darker brown. Now that's an effect you see quite often with colored minerals in thin section when you look at them with analyzer out. It's called pleochroism. This is biotite mica, and it's one of the most pleochroic of all minerals. All micas have this fundamentally layered internal arrangement of their atoms and ions. They all have a very well-developed cleavage parallel to these layers, which are planes of weakness in the structure. And this is a large and rather irregular crystal of biotite mica. And you can see the cleavages on this edge. Now then, imagine what you'd see if you were to cut a two-dimensional section through this mica at right angles to the cleavage. You'll see something like this, a rather irregular crystal, because well-shaped crystals are pretty rare in rocks. These black parallel lines are the cleavage traces, and this crystal is strongly pleochroic. And the darkest color comes when the cleavage traces are east-west, the palest color when they're north-south. And with the analyzer in, nice bright interference colors. And of course, 4 extinction positions 90 degrees apart. And they come when the cleavage traces are east-west and when they're north-south. Now let me show you another field of view. With the analyzer out, here's another crystal of biotite just like the last one. The cleavage traces, and it's pleochroic. But now, look at this crystal. Don't worry about these black dots, they're just minute inclusion in the crystal. But now watch what happens as I rotate the stage. There's hardly any color change in this one. It stays more or less uniform brown throughout a complete rotation of the stage. And what's more, you don't see any cleavage traces in this one. And with the analyzer in, no nice bright interference colors, just a rather murky grayish brown. This crystal is in fact all but isotropic. And at first you might think that that's a different mineral, but actually it's still biotite mica, only this time cut virtually parallel to the cleavage. And that's one of the nicest examples of the way in which the optical properties of minerals can change depending on the way that the thin section cuts through them. Now, all anisotropic minerals show some variation of optical properties with orientation. Let me show you a couple more examples. This is a model of a crystal of the mineral pyroxene. It's a rather idealized model, and you won't often find crystals as well-shaped or indeed as large as this in rocks. Now, pyroxene has got 2 cleavages at right angles. So, if you were to cut pyroxene like this, you'd see 2 sets of cleavages at right angles. But if you cut pyroxene like this, then, of course, all you'll get is 1 set of cleavage traces. So, although pyroxene has got actually 2 cleavages, you don't by any means always see 2 sets of cleavage traces in thin section. But in fact, the cleavages of pyroxene don't show up too well in thin section anyway, and mostly you'll only be seeing just 1 set of cleavage traces. But if you're lucky, in some crystals that are cut perpendicular to the 2 sets, you will in fact see 2 cleavage traces at right angles to one another. But that's a lot less common. And I want to use pyroxene as an example of something else. In thin section, with the analyzer out, pyroxine's a pale-colored mineral. And here, it's standing out from this colorless background because it's got high relief. And with the analyzer in, some of these pyroxene crystals show nice, bright interference colors. Others show much duller colors. They're all pyroxene, but they show a range of interference colors. Now, pyroxene's characterized as a mineral that has bright interference colors. And in thin section, mostly, you'll see grains with bright colors. But a few grains will have these much duller colors. And that's because interference colors are another property that varies with orientation in thin section. And now, just before I leave this, interference colors have nothing at all to do with the natural color of the mineral. Well now, what about this colorless background to the pyroxenes, this low relief material? Well, that's feldspar, and the feldspars are the most important group of rock-forming minerals. Now let me start with a simple example. Most feldspars, nearly all feldspars, show some kind of twinning, and this is the simplest kind. The crystal's effectively in two halves that are in different orientations, and they're joined across this plane that's called a twin plane. This is an example of simple twinning. Now imagine what you'd see if you were to cut a section like that, perpendicular to the twin plane. The crystal's in two halves, and as you rotate the stage, they go into extinction in different positions. And that's because the two halves are oriented differently, and so they polarize light in different directions. But now look at this one. There's no sign of any twinning at all. And that's because this crystal has been cut parallel with the twin plane. An important variety of feldspars is the plagioclase feldspars. And in thin section, they look like this with the analyzer in. Plagioclase feldspars are characterized by small-scale repeated or multiple twinning, and that's why you get this stripy effect when you look at them with the analyzer in. The stripes aren't always of uniform width, nor are they parallel-sided. But as you rotate the stage, you can see alternate sets of stripes or lamellae go into and out of extinction. And of course, if you cut plagioclase feldspar parallel with the twin plane, then you don't see any stripes. Well, I hope that these few examples have given you some idea of the way the optical behavior of minerals, of anisotropic minerals in thin section, depends very much on the orientation the thin section cuts through them.